Young little minds, welcome to another session of a physics all force e-learning program. This is physics session number 65. Well, in this session let us start a new chapter, a new topic called capacitors. So from today onwards let's talk about the chapter capacitors, a very important chapter, very important with respect to any entrance examination. You know, there is no entrance examination without a word called as capacitor. No entrance examinations regarding 10 plus 2 where the physics subject is involved, there will not be any paper without a term called capacitor. It's a very important topic. So let us understand the basic necessity of a capacitor, what are all the basic properties, all these things. Okay, so before going to that, let's have a recall. What are all the various things that are necessary to understand this concept? When I was telling you, charge is a fundamental property of matter. Q, charge units. We have taken the methods of charging. There are three methods of charging: charging by friction, charging by conduction, and charging by induction. You know, charging by conduction, charging by induction, these two are very important to understand this concept. Charging by conduction, one charged body connected to another charged body, either direct contact or indirect contact, the charge is shared. Same thing even in a capacitor. When one capacitor is connected to another capacitor, the charge stored on the capacitor is shared. Similarly, charging by induction, right? When a neutral body is brought very nearer to the charged body, then due to electrostatic induction, charge is induced. Even in this one also, a charged plate, if I get a plate very close to it, then because of the electrostatic induction, the charge on the charged plate will induce opposite charge on the opposite plate. This combination acts as a parallel plate capacitor. So that way methods of charging are useful in this one. Next, then later we have studied the force, Coulomb's force, F is equal to Q1 Q2 by R square. Right? Well, that is applicable for point charges. So here we don't deal with point charges. Then electric field, the space where the effect of the charge is felt, there are lines of force in the space. The field due to this capacitor, you have to understand. Force is electric field intensity is force experienced per unit charge. E is equal to F by Q. So to understand the electric field here, you need to apply this force. F is equal to EQ formula. Well, different electric field due to different charges we have learned. Electric flux we have learned, the measure of number of lines of force. Then the count of measure of number of lines of force passing through the surface is electric flux. Then according to Gauss law, when I consider a Gaussian surface, the total flux emerging from it is proportional to the charge that is inside the Gaussian surface. Right? Then using electric flux, we have derived the formula for the electric field due to linear charge conduct continuous charge distributions. Linear charge, plane charge sheet, charged sphere, non-conducting sphere, conducting sphere, hollow sphere, solid sphere. Right? You can derive the formula for many things. For a ring, disc, all this, using that you can find out. Later we have studied about electric potential. Potential is the state of a body which determines the electrical state of the body which determines the direction of flow of charge. Potential is very important to understand this concept. Potential is the state of the body, electrical state of the body, which explains the energy possessed, its stature, its electrical stature, level. Electric level is actually potential. In ordinary terms, it can be referred as electric level. So electric potential, by definition, it is the work done in moving a charge from infinity to the point. V is W by Q. Potential difference, work done to move a test charge from one point to another point. A unit positive charge from one point to another point. Potential difference. Later we have derived a formula for the potential due to point charge. Well, we don't consider point charge here. Right? Potential due to, we have derived the formula for the potential due to a linear charge, plane charge sheet, potential due to a sphere, hollow sphere, solid sphere, so on and so forth. Potential energy, we have even learned energy. The energy, the work done in moving a charge. So whenever you charge a body, you get a charge nearer to it, you have to spend energy. The external agent has to do work in moving the charge. So when you spend energy, the energy stored. Now the energy stored is potential energy, which is the most important point regarding this concept. What is a capacitor? It is the It is a device which is used to store that electrical potential energy. Whenever you are moving a charge nearer to another charge, the external agent has to do work. In doing work, it has to spend energy. The energy spent is stored. Now, where do you store? You store in a device called capacitor. So, capacitor is an electrical device which is used to store electrical energy in the form of electrical potential energy. It is an electrical element, an element which is used to store energy. Now, how do you store energy? You store energy by storing charge. You know, in our previous thing, we have taken a derivation. The self energy of a charged sphere, the self potential energy of a charged sphere. In the process of charging the sphere, right, by one elementary element of charge to by another element of charge, we were giving charge one by one element. Each element first dq, then another dq, we were adding. In the process of adding this charge to that sphere, you are doing work. There is work done, energy spent. All the energy spent is stored. It is stored in the form of electrical potential energy. Now it is stored in the form of a potential energy. That was the self energy of the sphere. So this way, whenever you store charge, there is energy stored. Our major point is to store energy. Well, you store energy by means of charge. So this electrical element which is used to store charge is termed as a capacitor. Well, capacitor, there are many types of capacitors. Capacitor, in the process of the development, many different types of capacitors come down. Now we use condensers. Well, the only single charge capacitor, it is outdated. Now we use the combination of charges, combination of continuous charge distribution. Then this is called condenser. Let us understand the capacitor concept and its capacitor. So capacitor is a device which is used to store electrical potential energy by means of charge. So when you are storing charge, indirectly you are storing energy. A capacitor is like a container. It is like a container which is storing charge. It's like a tank which is storing water in our general terms. Analogous. Let us imagine a tank. We are storing some water in it. Then a tank is a container which is storing water. Right? Whenever we are in need of it, we will make use of that water there. Whenever you store water, water will have a level. According to its level, it will have energy. Gravitational potential energy. Similar to it, charge. A container which is used to store charge. So when I am storing charge, I am storing electrical potential. Whenever I am in need, I can make use of this charge. So that way, when I am in excess of charge, I want to store. I want to use it when I am in deficit of it. So to store this charge, I need an element. The element that is used to store the charge and energy, of course. Store energy in the form of charge and use it whenever you are in need. That element is a capacitor. There are different types of capacitors. First, a sphere, a charged sphere. When I take a charged sphere like this of radius r, I am storing charge. A simple capacitor. A simple spherical capacitor. Well, this spherical capacitor, it is of bigger size, but the charge stored is less. Right? So there was a necessity of changing its format, its composition, its arrangement, all this. By changing it without increasing the size, I am able to increase its capacity. Now that changed version is called condenser. Right? So we will talk about this. Now coming to the capacitor, so let us define the capacity. Suppose there is a tank which is storing water. So what is the capacity of the tank? How much water it can store? So similarly, we can define how much charge it can store. The parameter which defines the capacity of that capacitor, now that is called as capacitance. It's termed as capacitance, or simply you can call it as it is the capacity of a capacitor. Capacitance or capacity of a capacitor, capital C. Just C, it's a scalar. It actually refers to the ability of the body to store charge, how much it can store charge. So how much any container can store water? For example, if I take a tank, how much water it can store? As I pour water into it, the water level increases. As I put on more water, as the mass of water increases, the level of water increases. So as similar, as I store charge on a capacitor, its electric level increases. I mean the potential increases. So the charge stored on a capacitor in a container is directly proportional to its potential. Suppose if you look upon a tank, if the tank is fully filled, so level is filled, charge is more water is stored. Had the level been half the water is stored. So you calculate the measure of amount of water by its level. Similarly, the measure of charge by its electric level called potential. So the charge stored in a capacitor is directly proportional to potential. So the proportionality I have to remove. So Q is CV. Well, C is called as, this C is called capacity of a capacitor. Capacity of a capacitor, or just simply, or you can call it as capacitance. It's called capacitance. So Q is equal to CV. Now from this I can write the capacitance C as Q by V. Capacity, it is a constant of proportionality, please. So constant of proportionality C, it neither depends on charge nor depends on potential. It's a constant of proportionality. It depends upon the shape of the capacitor, size of the capacitor, the medium that is being used, right? So various parameters, but it neither stores on charge nor it neither depends on charge nor on potential. So the amount of charge stored in a capacitor Q directly proportional to the electric level or potential. So Q proportional to V, Q is equal to CV. C is called capacity of a capacitor or capacitance. So C I can write as Q by V. Well, how do you define C? Let V equal to 1 volt. Then I can write C as Q. So I can define the capacity of a capacitor. It can be defined like this. It is the amount of charge that can be stored in it at unit potential. When the potential is 1 unit, what amount of charge is stored in it? Now this is termed as the capacity of a capacitor. So when V is equal to 1 volt, put here V1, then C is Q. So just put it in proper terms. Capacity of a capacitor is the amount of charge that is stored in a capacitor when the potential is 1 volt. At unit potential, 1 volt potential. For unit potential, how much charge it can store? For every 1 unit potential, how much charge it can store? That is termed as capacity of a capacitor. How do you measure it? So charge, of course, it is measured in coulombs. This is measured in volts. Coulomb per volt, this is called farad. The SI unit, farad. Well, in CGS unit, charge is measured in ESU, stat coulomb, and the voltage is measured in stat volts, and this is stat coulomb. Well, this is called stat farad. CGS unit. Stat coulomb per stat volt is stat farad. Well, we will not be using much of this. We use, in major cases, we use farads. But you know, this farad is a very big unit. In our environment, farad is a very big unit. So in our environment, we are in need of tiny capacitors. So we go for millifarad or microfarad or nanofarad or picofarad. Right? So these are the submultiples: millifarad, microfarad, nanofarad or picofarad. So that way the submultiple of the farads we use. Farad is a very big unit. A capacitor is like a element which is used to store charge. If vast amount of charge can be stored, then you can put it as farad. Farad is so big, it's beyond our necessity actually. So we go for milli, micro, nano and picofarads units. CGS is stat farad. Stat coulomb by stat volt is stat farad. Well, here in this one, if I take 1 coulomb by 1 volt, then this is 1 farad. If there is a capacitor which is storing 1 coulomb for every 1 volt potential, then its capacity is equal to 1 farad. For every 1 volt potential, if 1 coulomb charge is stored in it, then its capacity is 1 farad. Unit capacitance 1 farad. 1 coulomb per 1 volt is 1 farad there. Is it? No. So units, it is a mere number, it's a constant. It's a mere number, it's a scalar. It has no direction, it is a scalar. Well, how about the direction? You know, it's a scalar, it has no direction. It's dimensional formula. That dimensional formula of capacity, you know, charge is current into time dimensionally by potential. You know, potential is work done per unit charge. Work done, it is ml square t minus 2 by charge, that is it. So when I take this up, so capacity as the dimensional formula m minus 1 l minus 2 and this, it is t power 4 I square. So this is the dimensional formula. You know, capacitance m minus 1 l minus 2 t power 4 I square. The significance of this is mass dimension is negative. Usually many physical quantities do not possess mass dimension negative. Very few, out of which this is one of it. Really electrical, it's an electrical quantity whose mass dimension is negative. You can remember it as an electrical quantity for which the mass dimension is negative. Something peculiar, different. So it's important. Can be asked in entrance examination. So m minus 1 l minus 2 t power 4 I square is its dimensional formula. It's a scalar, right? It's measured in farads. Well, we go for some multiples, tiny units, milli, micro, nano farads, picofarads. Well, 1 coulomb is defined like this, 1 volt. So charge Q, if the capacity is C, potential is V, so charge Q is CV. Or capacity C, you can write as Q by V. Well, reciprocating this V, I can write as Q by C. So these are the 3 things by which you can make out the capacity of a capacitor. So a capacitor is a device which is used to store electrical energy in the form of charge. There are different types of capacitors, different capacitors are there. Well, we will be learning about the capacity of each and every this thing. In our topic, we will be learning about different types of capacitors. Then, how much capacity, the measure of the capacity of a capacitor. Now, this is termed as capacitance, or it is capacity of a capacitor. It's termed as capacitance or capacity of a capacitor. Right? So, capacitance. So actually the charge stored in a capacitor depends on its electric level, that is potential. So the charge is directly proportional to potential. C is equal to QV. If I draw a graph between Q and V, the charge stored in a capacitor with the potential, it's a straight line passing through the origin. Right? So as the potential increases, charge increases the graph. Right? So therefore, the charge. If you take the slope of the graph, tan theta Q by V, the slope of the graph represents C capacity. So the proportionality constant is C. So C is equal to Q by V. It is defined as the amount of charge that is stored in a container at unit potential. For 1 volt potential, what amount of charge is stored? The amount of charge stored for 1 volt potential is termed as the capacity of a capacitor. Charge per 1 volt. Right? So coulomb per volt is farad units. Well, 1 coulomb by 1 volt is 1 farad. 1 farad capacity of a capacitor. A capacity of a capacitor is 1 farad. It is said to be 1 farad if it is storing 1 coulomb charge for every 1 volt potential. For every 1 volt, 1 coulomb charge. Its dimensional formula m minus 1, very peculiar. Please remember m minus 1 l minus 2 t power 4 I square. So this way you can understand a capacitor, the definition for a capacitor, and its parameter showing the measure of the capacity, its measure of its quantity, the index of its thing. It is termed by the capacity of the capacitor or capacitance. So this way it is. Now understanding from this formula, suppose if I take C is equal to Q by V, let us understand this formula carefully. Suppose if I take the formula C is equal to Q by V, now a capacitor, a container. The amount of charge stored in a container, for a particular container, the amount of charge stored depends on potential. More the level, more the charge. So for a particular container, charge is proportional to potential. Right? For a particular container, Q proportional to V. As V increases, Q increases. As V decreases, Q decreases. Directly proportional. So for a particular container, I can write when Q, it's Q1 by Q2 is equal to V1 by V2. When C is constant. When C is constant. But coming to this formula, Suppose if two different containers, same charge is taken in it. There are two different containers, same amount of charge is taken in. Charge is same, then the level, potential and capacity both are inverse. There are two containers, same charge is taken in. The electric potential of one is big, the other one is small. Right? The electric level of one is, in one container is big, but the other one is less. So here level is big. Now the capacity of that capacitor is less. So when for the same charge, capacity varies inversely with potential. Different containers for same charge, if the potential is more, then its capacity is less. If the potential is less, capacity is more. So when the charge is same, when Q is same, so this is when C1 is equal to C2, you can write like this. But when Q1 is equal to Q2, when charge is same, Q1 is equal to Q2, then you can write C1 V1 is C2. Well, similarly, suppose if there are two containers, the level potential is same. If the potential is same, then charge proportional to its capacity. When charge is same, potential inversely proportional to capacity. When capacity is same, Q directly proportional to V, so Q1 by Q2, V1 by V2. When charge is same, V inversely proportional to C, C1 V1 is C2 V2. And when potential is same, when V is same, V is a constant, then Q proportional to C, Q1 by Q2 is C1 by C2. For same electric potential, right, bigger container will have more charge, smaller container will have obvious. For the same potential charge, we have learned this in charging by conduction. When I was sharing charge for two different containers by putting them in contact in the sense the potential is same. So the container with the sphere with more radius, size, more charge. The charge was proportional to size capacity. So charge depends on size. For the same potential, when the potential is same, charge proportional to capacity. Q1 by Q2 is C1 by C2. Well, when charge is same, potential, for different containers, same charge is given. Smaller charge, smaller container, the smaller capacitor will have more potential. It will attain more level. So that way we can visualize the things there, right? You can understand. It is as simple as like imagining a tank. Let's suppose there are two tanks, right? Two identical, similar tanks. Then same capacity. In one tank the level is more, in one tank the level is less. So the tank with more level, it contains more water, less level, less water. Similarly, if I imagine two different containers, same water is poured into it. Well, in a bigger container, same water will have lesser level, but in a smaller container, the same water will have more level. So for same charge, level inversely proportional to capacity. Similarly, for two different containers, if I pour water to same level, then the bigger one will have more charge, more water, smaller one will have less water. So this way, pertaining to which constant? It's not like, this doesn't mean C proportional to Q. Capacity does not is not directly proportional to charge stored. You can take down the ratio, right? So that way, we can write down the things in regarding the proportionality regarding the charge there. Okay, right? So this is regarding capacitor, capacity of a capacitor, the amount of charge stored in it, the measure of its capacity called capacitance, its units, its dimensional formula. Well, it's a scalar, it has no direction, it's a mere number, it's a constant of constant. The graph QV, graph is a straight line passing to the origin, and the proportionality like this. Okay, you can understand. Well, later we will go for different types of capacitors. Thank you. Capacitors are of various types. Suppose if I take a sphere, a metal conducting sphere of radius r, I am giving charge to it, then this is called as a spherical capacitor. Simple, a spherical capacitor. But if I take a combination of two concentric spheres, metal spheres, and make some small arrangement, then it's called as a spherical condenser. Well, a combination of two spheres, metal conductors, well, outer one being earthed, then it's a spherical condenser. Well, why this we'll be learning about in the next. Similarly, a combination of two parallel plates, one being given positive and the other one is this is called as a parallel plate capacitor. Similarly, a combination of a cylinder, conducting cylinders like this, the outer one being earth. This is called cylindrical capacitor. So this way there are many types of capacitors. In industrial purpose, in industry, we use many different types of capacitors called multiple capacitors, right? Then paper capacitor, then spherical capacitor. There are many such electrolytic capacitor. We have got many such other types of capacitor. But basic we learn from these things, right? So first we shall have an idea about a simple capacitor. Instead of going for a condenser, actually this is a parallel plate condenser, spherical condenser, parallel plate condenser, cylindrical condenser. But since the single element being used, it is outdated, now we are terming them as capacitors. But actually the basic capacitor, the basic fundamental capacitor is a sphere. A simple sphere, a conducting sphere of radius r. When charge is given to it, charge will be stored on its surface. Some charge q is stored on the surface like this. Then from this you can even evaluate the capacity of a capacitor. As the developments poured in, the size is reduced and the capacity of a capacitor was increased. Earlier, a big sphere used to have a very small, minute capacity. But as the developments poured in, or as people researched on it, the size was reduced and the capacity of the capacitor was increased. In a small, tiny, simple box, you can have some millions of capacitors, multiple capacitors being put up inside, and the capacity is increased multiple times. So that way, the capacitor has changed from the initial stage to now the modern level. It has changed abruptly. The basic capacitor is a sphere. It's a sphere, a spherical capacitor. It's a basic thing. So first given charge is stored on it, then from this we find the potential from which we make out the capacity of a capacitor. Right? In the next session, we will talk about the different types of capacitors, their capacity and their illustrations, their applications, so on and so forth. So in this chapter, in this session, we have learned about the capacitor. What is a capacitor? A device which is used to store charge and energy. Well, actually the main purpose is to store energy. We store it in terms of charge. Right? Capacity, the measure of its capacity, its ability, how much? The measure is capacity of a capacitor or capacitance. It is, the charge stored in a capacitor is directly proportional to the potential, electric potential. So Q proportional to V, Q is Cv. So C is Q by V. Units, farads. Dimensional formula m minus 1 L minus 2 T power 4 I square. It's simple, it's a scalar. So these are the things there. In the next session, we will talk about the different types of capacitors. Right? Thank you.